Could the final remnants of intelligence outlast even the stars themselves? Such questions might seem fit only for the musings of science fiction, yet they rest upon foundations laid by our most profound scientific discoveries. 100 trillion years into the future, a span so vast it stretches imagination, the universe will have aged into desolation. The stars, those brilliant engines of creation, will have long since extinguished their fires. In this unfathomable epoch, the universe's dwindling energy will give rise to an era of endless darkness, where entropy reigns supreme. In the twilight of time, imagine a species that once reshaped entire star systems. They were masters of their domain, dismantling planets and mining asteroids to construct a sprawling interstellar empire. But their era of glory was destined to fade. With the passage of millennia, they faced the harsh truth: the universe itself was dying. Star by star, the cosmos dimmed, leaving behind only black holes and the faint, residual glow of thermal radiation. Faced with the inevitability of cosmic decay, these beings undertook one final, monumental engineering feat around a solitary black hole. They built their ultimate refuge, a thin, vast shell forged from the wreckage of worlds. Within this enclosure, they found a fragile sanctuary. The black hole, a remnant of a long-dead star, became their paradoxical savior. It provided not just energy, harnessed from the accretion of infalling matter, but also the most precious resource of all, time. Here, within the immense gravitational pull of the black hole, the fabric of spacetime itself was distorted. This is no speculative fancy but a consequence of Einstein's general theory of relativity. The closer one approaches an intense gravitational field, the slower time flows relative to distant observers. To those within their engineered haven, time trickled at a glacial pace, stretching moments into millennia. While the universe outside accelerated toward heat death, they experienced only the barest passage of time. This remarkable manipulation of time reflects one of the profound insights Einstein revealed over a century ago: time is not absolute. It bends and stretches, depending on the interplay of gravity and velocity. To us, accustomed to thinking of time as a steady, universal rhythm, this is nothing short of revolutionary. But for the final survivors of this imagined civilization, it was the key to extending their existence against the vast, uncaring tide of entropy. Yet, for all their ingenuity, they knew this was only a delay. The relentless pull of the second law of thermodynamics guaranteed that even their black hole would eventually evaporate via Hawking radiation, its energy dissipating into the cold void. In the end, the universe would achieve a maximum entropy, a state of perfect stillness and unchanging darkness. Their sanctuary, like everything else, would succumb to the silence. This speculative narrative, while fictional, invites us to explore questions grounded in real science. What is the ultimate fate of the cosmos? What role does gravity play in shaping not only space but also the passage of time? Einstein's work on relativity shattered the classical notions of time and space as fixed and immutable. Instead, he showed that spacetime is a dynamic, interwoven fabric, molded by the presence of mass and energy. But these discoveries, awe-inspiring as they are, also raise profound questions. What is the true nature of time? Is it an intrinsic feature of the universe, or a construct of human perception? And as we probe deeper into these mysteries, will we unveil ultimate clarity, or will the essence of time and space elude us further? What is space? Can you imagine standing still while the world around you spins? Can you feel motion when there are no points of reference? These questions have tantalized human minds for millennia, inspiring wonder and driving the relentless pursuit of understanding. What is this vast, invisible stage on which the drama of existence unfolds? At first glance, space seems simple: a backdrop, an empty void, a platform for stars, planets, and lives to inhabit. But delve deeper, and the simplicity dissolves into mystery. Space is not merely the absence of matter, it is a concept that underpins everything we see, touch, and experience. What, then, is its true nature? The earliest thinkers wrestled with this enigma. In the 4th century BCE, Plato described space as the nurse of becoming, a medium that allows everything to exist yet possesses no properties of its own. His student, Aristotle, dismissed the notion of a true void, arguing instead that space was intrinsically linked to the objects within it. For over 2 millennia, this philosophical view held sway, but it provided little clarity about space's deeper nature. By the 17th century, the tides of understanding began to shift. The universe, once explained through myth and metaphor, started to yield its secrets to the language of mathematics. Galileo Galilei, a giant of this era, laid crucial groundwork for our comprehension of space through a simple thought experiment, a sailor locked in a windowless cabin on a boat. Imagine this sailor, unaware of the world beyond their enclosed space. When the ship is still, the cabin is serene, plates remain steady, and a goldfish swims peacefully in its bowl. But if the ship begins to move uniformly, the sailor notices no change inside the cabin. Plates fall straight down when dropped, and the goldfish remains undisturbed. Galileo realized that there is no experiment the sailor could perform to distinguish whether the ship is at rest or moving uniformly. From this, Galileo concluded that motion is not absolute, it is relative. Any uniform motion feels indistinguishable from rest, a revelation that formed the first seeds of the theory of relativity. This new understanding of motion laid the foundation for a monumental debate between two of history's greatest minds, Isaac Newton and Gottfried Wilhelm Leibniz. For Newton, space was an immutable stage, an absolute entity existing independently of matter. He argued this with the famous spinning bucket thought experiment: spin a bucket of water, and the surface curves. To Newton, this curvature arises because the water spins relative to absolute space, a universal framework that exists even in a universe devoid of objects. Leibniz vehemently disagreed. For him, space without matter was meaningless. Space, he argued, exists only as the relationship between objects, much like time exists only to describe the sequence of events. Without objects, there could be no spatial framework. Newton's view ultimately prevailed, shaping the scientific consensus for nearly 2 centuries. His Principia Mathematica enshrined the concept of absolute space and time, a vision of the cosmos where events unfolded on an unchanging, universal stage. Despite Newton's triumph, Galileo's principle of relativity endured. Absolute space might exist, but absolute rest, an unmoving reference point, was unattainable. Motion remained inherently relative, an idea that continued to challenge scientific thought. But what of time? Newton envisioned time as a universal metronome, ticking evenly across the cosmos. A second on Earth was identical to a second on the farthest star. Yet this assumption, too, would eventually be questioned. Space and time, these twin pillars of existence, remained shrouded in uncertainty. Were they immutable frameworks, or were they shaped by the objects and events within them? Could time flow independently of the universe's happenings, or was it as malleable as space itself? These questions would lead humanity on a journey of discovery, from the heat of thermodynamic systems to the revolutionary insights of Albert Einstein. The answers, it turns out, are far stranger than Newton or Leibniz could have imagined. And so, the quest to understand space and time continues, each revelation bringing us closer to the heart of a mystery so profound, so beautiful, that when we finally grasp it, we may wonder how we ever saw the universe any other way. Imagine a universe, countless trillions of years in the future, where the stars have all gone out, and only the faint hum of black holes remains. Around one such black hole, the remnants of a once great civilization linger, clinging to existence in a cosmos growing ever colder and darker. They sit, they wait, because waiting is all they can do. The march of time, inexorable and unforgiving, has left them with one haunting realization: their greatest enemy is not the failing cosmos, but time itself. You may see a cup of tea fall from a table, shattering into pieces, they reflect, but you will never see the pieces leap back together to form the cup. Time surrounds us, defines us, yet eludes our grasp. Unlike space, which we can traverse freely in multiple directions, time holds a firm grip, dragging us from past to future along a single path. Why does time flow? Why does it have a direction? And why does it seem so inextricably tied to change, decay, and the loss of order? Ancient thinkers wrestled with these questions. Aristotle defined time as the measure of change, the steps between before and after. Hindu philosophers envisioned it as cyclical, with creation and destruction repeating over immense cosmic eras. Yet for all their insight, time's essence remained a mystery. Time appears as an ever-present backdrop, much like space. Yet it is a different beast entirely. Its unidirectional flow and connection to entropy make it far less forgiving. While scientists might pragmatically treat time as just another variable in their equations, this approach ignores its profound and peculiar nature. To truly understand time, we must first examine a most unexpected source, the steam engine. The Industrial Revolution brought with it a curious question: how much work can you extract from a machine? With horses and oxen, the calculation was simple: feed them well, and they work hard. But with steam engines, powered by coal, the equation grew more complex. Could machines rival the efficiency of animals, or would they always be limited by waste? This dilemma gave birth to thermodynamics, a field devoted to understanding energy and its transformations. Early engines were woefully inefficient, converting only a fraction of their fuel's energy into useful work. The rest was lost as heat, radiating into the surroundings, or dissipated through friction as metal ground against metal. Perfect efficiency, it turned out, was an illusion. The laws of thermodynamics revealed why. Energy, as it flows through any system, inevitably becomes more disordered, a phenomenon measured by a concept called entropy. As energy disperses, systems move from order to disorder, not because it is physically impossible to reverse the process, but because it is staggeringly improbable. In the 19th century, James Clerk Maxwell envisioned a thought experiment that challenged these ideas, a demon capable of sorting fast-moving gas molecules from slow-moving ones. By separating hot molecules from cold, the demon could seemingly defy entropy, creating order where there was once disorder. Yet, as debates raged for over a century, it became clear that even the demon could not escape thermodynamic laws. Sorting molecules requires information, and the act of forgetting that information, the erasure of memory, creates waste heat, contributing to entropy. This irreversibility is key to understanding time. Every action, every event, every forgotten memory generates disorder, pushing the universe further along a one-way path. Entropy provides a physical basis for the arrow of time, anchoring our sense of yesterday and tomorrow in the inescapable reality of decay. If entropy defines time's arrow, what happens when the universe reaches its end? Lord Kelvin, a pioneer of thermodynamics, foresaw a grim conclusion: the heat death of the universe. In this scenario, all usable energy is spent, leaving a cosmos in a state of maximum entropy, cold, dark, and unchanging. With no gradients of energy to drive motion or events, would time itself cease to have meaning? The implications are profound. If time's flow is tied to the irreversibility of processes, then in a universe where no processes occur, time might lose its very essence. Modern science has revealed deeper links between entropy, information, and energy. In computers, for example, processing information generates heat, not merely because of the calculations performed, but because of the act of forgetting. Each erased bit of information adds to the universe's entropy, a phenomenon experimentally confirmed in 2012. This process, while minuscule, is unavoidable, suggesting that the simple act of thinking, calculating, or remembering contributes to the cosmos' inexorable decay. And so, we return to our imagined civilization at the end of time. Around their dying black hole, they sit in stillness, preserving every ounce of energy as the universe marches toward its inevitable fate. With entropy at its peak, the cosmos will fall silent, a vast and unchanging expanse. In this ultimate stillness, would time remain? Fundamental physics does not yet hold a definitive answer. But perhaps the future, as we imagine it, is only possible because we cannot forget the past. Perhaps the very concept of tomorrow is inextricably tied to the loss, decay, and irreversibility that make time flow. Yet, as we ponder these questions, a new revolution in our understanding of time and space beckons, a transformation that may lead us to the last days of our lonely cosmos and reveal the ultimate nature of existence itself. New space. For millennia, humanity has grappled with these questions, weaving myths and theories to make sense of the vast expanse above. Yet, it is only in the last few centuries that we have begun to unravel the secrets of space itself, revealing a reality far stranger and more beautiful than we could have imagined. In the twilight of a dying civilization, sheltered within the event horizon of a black hole, a few curious minds dared to ponder the universe. Their dwindling energy did not extinguish their thirst for understanding. Instead, they turned their gaze inward and outward, reflecting on the fundamental nature of space, that enigmatic entity which defines distance, shapes movement, and cradles the stars. Central to their musings was the story of light. Light, with its unimaginable speed, had long been a cornerstone of scientific discovery. It was light that revealed the scale of their empire and light that set an immutable boundary they could never surpass. For centuries, the speed of light had been a mystery. Early experiments revealed it was faster than sound, but was it infinite? This question was definitively answered in 1676 by the Danish astronomer Ole Romer. Observing the moons of Jupiter, Romer noted discrepancies in their eclipses, discrepancies that correlated with Earth's changing distance from Jupiter. From this, he deduced that light must travel at a finite speed, a revelation that reshaped our understanding of the cosmos. His calculations, refined by Christian Huygens, estimated light speed at over 211,000 kilometers per second, remarkably close to the modern value of approximately 300,000 kilometers per second. Yet, even as light speed was measured, its nature remained elusive. The 19th century brought James Clerk Maxwell's groundbreaking work, which unified electricity and magnetism into a single theory of electromagnetism. Maxwell's equations revealed that light is an electromagnetic wave, a self-propagating interplay of electric and magnetic fields, moving at the speed enshrined in his equations. But this raised a profound question, relative to what does light travel? Physicists of the time hypothesized that light required a medium, an invisible ether, permeating the cosmos. This ether, they believed, would provide a universal frame of reference, an ultimate state of rest. However, this idea clashed with Galileo's principle of relativity, which held that the laws of physics are the same in all inertial frames of reference. The search for ether produced no results, leading to a crisis in understanding. Enter Albert Einstein. In 1905, Einstein proposed his special theory of relativity, a radical rethinking of space, time, and light. He declared that the speed of light is constant in all inertial frames, irrespective of the motion of the source or the observer. This simple yet profound postulate overturned centuries of Newtonian mechanics, where velocities could be added and subtracted. Einstein's insight demanded a fundamental change in our understanding of space and time. To preserve the constancy of light speed, space and time themselves had to become relative, dependent on the observer. Distances could contract, and time could dilate, reshaping the fabric of reality. The implications of Einstein's theory were profound but incomplete. In 1908, Einstein's former professor, Hermann Minkowski, introduced a new conceptual framework, spacetime. Minkowski combined the three dimensions of space with the single dimension of time into a unified four-dimensional continuum. In this spacetime, events are points, and their relationships are governed by geometry. The geometry of spacetime elegantly explained the transformations between observers, solidifying relativity as not just a theory of motion but a theory of reality itself. Minkowski's vision set the stage for Einstein's next leap, general relativity. Over a decade of intense work, Einstein extended his theory to include gravity, proposing that mass and energy warp spacetime, creating the effects we perceive as gravitational attraction. In this new paradigm, gravity was no longer a force but a manifestation of spacetime's curvature. The first solution to Einstein's field equations came from Carl Schwarzschild in 1916. Schwarzschild's work revealed that a sufficiently massive object could collapse into a singularity, a point of infinite density surrounded by an event horizon. This was the mathematical description of a black hole, a region where spacetime's curvature becomes so extreme that not even light can escape. Near a black hole, time itself slows, as predicted by general relativity. An observer far from the black hole would see a clock near the event horizon tick more and more slowly. This time dilation exemplifies the malleability of spacetime, a concept confirmed by numerous experiments, including the famous Haffel-Keating experiment of 1971. By flying atomic clocks on jet planes and comparing them to ground-based clocks, physicists demonstrated that motion and gravity affect the passage of time, precisely as Einstein had predicted. Einstein's equations also hinted at another phenomenon, gravitational waves. These ripples in spacetime, caused by the acceleration of massive objects, remained theoretical until 1974, when Russell Hulse and Joseph Taylor discovered a binary pulsar system. The gradual decay of the pulsar's orbit matched predictions based on energy loss through gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves from merging black holes, opening a new window on the universe. These detections confirm that spacetime is not static but dynamic, capable of stretching and compressing as waves propagate through it. One of the most startling revelations of 20th century physics was that the universe itself is expanding. This discovery, rooted in the work of Alexander Friedmann and Edwin Hubble, showed that galaxies are moving away from each other, their speeds proportional to their distances. This expansion implies that the universe was once concentrated into an infinitely dense point, the Big Bang. As space expands, distant galaxies recede from us, some so quickly that their motion exceeds the speed of light. This does not violate relativity, as the galaxies are not moving through space, rather, space itself is expanding. This phenomenon creates a horizon beyond which light cannot reach us, defining the observable universe. Despite these breakthroughs, the true nature of space and time remains elusive. Are they physical entities or abstract constructs? General relativity treats spacetime as a flexible fabric, but quantum mechanics, which governs the microscopic world, suggests a more granular reality. Some theories propose that spacetime is emergent, arising from more fundamental principles, while others suggest it is woven from quantum threads. As we probe deeper, we encounter paradoxes and mysteries. The expansion of space raises questions about energy conservation, as photons lose energy through redshift and galaxies slow their motions. These phenomena defy traditional symmetries, challenging our understanding of fundamental physics. In the words of Nobel laureate Steven Weinberg, space itself is nothing. This statement, paradoxical yet profound, underscores the enigma of spacetime. It is the stage for all events, yet it lacks intrinsic properties. It can bend, ripple, and expand, but its essence remains intangible. New time. Is it a river flowing inexorably forward, carrying us on a current we cannot escape? Or is it a frozen tapestry, every moment existing at once, waiting for our consciousness to navigate its labyrinth? If time could speak, would it whisper the secrets of its beginning or the mysteries of its end? These are not merely philosophical musings but profound questions that have haunted physicists and philosophers alike, their answers lying at the nexus of science and imagination. In the civilizations of the far future, time was no longer a mere backdrop to existence. It had become an instrument, a malleable fabric woven into the very architecture of their society. Their engineers had mastered the subtleties of Einstein's spacetime, bending and shaping it to create gateways between distant stars and to witness cosmic finales in the slow, stretched moments near black holes. Time was both their servant and their muse, a duality that embodies the paradoxical nature of existence itself. Albert Einstein's theory of general relativity shattered the Newtonian view of time as a universal constant. Instead, time was revealed as elastic, stretching and contracting depending on speed and gravitational fields. A clock aboard a spaceship traveling close to the speed of light ticks more slowly than one on Earth. Near a black hole, the intense gravitational pull slows time to a crawl. This malleability of time has profound implications. It allows us to envision scenarios where one could, in principle, step outside the bounds of the present moment. But it also raises thorny questions about the nature of the past, present, and future. If time is relative, where does the present reside? Without a cosmic clock to dictate a universal now, how can we distinguish the past from the future? The mathematical framework of relativity suggests an unsettling possibility, the block universe. In this view, time is like a landscape, with all events, past, present, and future, existing simultaneously. Every particle in the universe traces a world line through this four-dimensional spacetime, charting its journey from the past to the future. This perspective challenges our intuitive understanding of time as a flowing river, forcing us to confront the possibility that free will and the unfolding of events might be illusions. Yet, our everyday experience contradicts the block universe. We remember the past and anticipate the future. We see broken eggs but never witness them reassembling themselves. This asymmetry, known as the arrow of time, is deeply ingrained in the macroscopic world. But where does it come from? The answer lies in entropy, a measure of disorder. The second law of thermodynamics tells us that entropy in a closed system always increases over time. The universe began in a state of extraordinarily low entropy, a smooth, hot, dense state following the Big Bang. As the universe expanded, gravity pulled matter into clumps, forming stars and galaxies. This transition from low to high entropy imbued the cosmos with its temporal direction. Physicist Roger Penrose calculated that the probability of the universe starting in such a low entropy state was 1 in, a number so staggeringly small it defies comprehension. This improbability hints at something profoundly special about the universe's birth, though its cause remains a mystery. At the microscopic level, the fundamental interactions of nature, electromagnetism, gravity, and the strong nuclear force, are largely indifferent to the direction of time. For instance, if you filmed two electrons repelling each other and played the footage in reverse, the interaction would still obey the laws of physics. The weak nuclear force is a rare exception, exhibiting a tiny preference for a particular temporal direction. This disconnect between the time-reversible laws of physics and the irreversible processes of the macroscopic world is one of the great puzzles of modern science. How does the arrow of time emerge from a foundation that is fundamentally indifferent to it? The answer may lie in the collective behavior of countless particles, their interactions giving rise to the thermodynamic arrow of time. The origins of time itself are tied to the birth of the universe. Before the Big Bang, our concepts of space and time break down. The universe's initial conditions were not only extraordinarily hot and dense but also extraordinarily smooth, a state that set the stage for the emergence of time's arrow. But what brought this state into being? Was it a quantum fluctuation, a collision of brains, or something entirely beyond our current understanding? Time's arrow may also be linked to the expansion of the universe. As space stretches, the entropy of the cosmos increases, and the directionality of time becomes apparent. This interplay between cosmology and thermodynamics ties the arrow of time to the very structure of the universe. If time is a dimension like space, could we travel through it? Solutions to Einstein's equations suggest tantalizing possibilities. Rotating black holes, wormholes, and other exotic configurations of spacetime could, in theory, create closed time-like curves, paths through spacetime that loop back on themselves. Such paths would allow an object to travel into its own past. In the 1940s, Dutch physicist Willem Jacob van Stockum demonstrated that a rotating universe could contain such closed time-like curves. Although his model was idealized and unlikely to describe our universe, it opened the door to serious scientific inquiry into time travel. Decades later, mathematician Kurt Gödel found another solution, showing that a rotating cosmos could permit journeys to the past. However, time travel poses paradoxes. The most famous is the grandfather paradox. What happens if you travel back in time and prevent your own birth? Such contradictions suggest that either time travel is impossible or that it operates under constraints we do not yet understand. While relativity describes the large-scale structure of spacetime, quantum mechanics governs the microscopic realm. Could the union of these two theories reveal the true nature of time? Quantum entanglement hints at a deeper connection between past, present, and future. When two particles are entangled, measuring one instantly affects the other, no matter the distance between them. This phenomenon appears to defy the flow of time, suggesting that time as we perceive it may be an emergent property rather than a fundamental feature of reality. The quest to reconcile quantum mechanics and relativity has led physicists to theories such as loop quantum gravity and string theory, each offering glimpses into the fabric of spacetime. Some propose that time itself is quantized, composed of discrete moments rather than a continuous flow. Others suggest that time emerges from a deeper, timeless quantum state, a concept that challenges our most basic intuitions. As we probe the nature of time, we find ourselves confronting questions that blur the lines between science and philosophy. If the block universe is correct, then every moment of our lives exists eternally, etched into the spacetime fabric. Free will may be an illusion, yet the choices we perceive as ours ripple through the cosmos, shaping the tapestry of eternity. In the end, time remains both a mystery and a muse. It is the stage upon which the universe unfolds, the thread that ties together the stories of stars and atoms, galaxies and people. Whether we are travelers tracing our world lines through a predetermined block universe or architects of our own destinies, the enigma of time continues to inspire and challenge us, inviting us to explore the boundaries of knowledge and imagination. Quantum spacetime. What is the essence of existence? How do we comprehend the fabric of reality, its vastness, its mysteries, its boundaries? These questions have haunted humankind since the dawn of thought. In the far future, when the stars have long dimmed and matter itself begins to dissolve into the cosmic abyss, such questions take on a poignant urgency. For those few remaining witnesses to the universe's twilight, the search for understanding becomes not just a pursuit of knowledge but a desperate attempt to find meaning in the final moments of existence. The distant future paints a grim picture. The stars, once vibrant beacons of light, have extinguished. Black holes, the mighty remnants of cosmic grandeur, have evaporated, succumbing to the relentless pull of quantum mechanics. Even the particles that make up matter itself are beginning to decay, leaving the universe a cold, dark expanse. Civilization, once teeming with life and purpose, now clings to existence in isolated enclaves. These remnants, scattered and weary, gaze at the last flickers of light from a dying cosmos, knowing that the end is near. Yet, despite the despair, there is something profoundly human in their gaze, a need to understand, to connect, to bear witness. The ancients had foreseen this end, their theories warning of the universe's inexorable march toward entropy. They knew that even the immense gravity of black holes, governed by Einstein's general relativity, could not withstand the quantum decay predicted by the probabilistic world of quantum mechanics. For centuries, physicists grappled with the divide between these two pillars of modern physics, general relativity and quantum mechanics. Relativity, the domain of the cosmic and the immense, describes gravity as the curvature of spacetime itself. Quantum mechanics, by contrast, governs the microscopic and probabilistic, where particles behave as waves and existence flickers between possibilities. These theories, each triumphant in their realms, seemed irreconcilable. The conflict was stark. A student attending lectures on general relativity in the morning and quantum mechanics in the afternoon might be forgiven for thinking the disciplines were crafted in isolation. Indeed, for over a century, they defied unification. The universe's most fundamental mysteries, the nature of spacetime, the origins of gravity, and the behavior of matter at its most basic, remained shrouded in paradox. Among the pioneers of quantum mechanics stood Paul Adrien Maurice Dirac, an enigmatic figure whose mathematical elegance reshaped physics. Born in 1902 in Bristol, Dirac's quiet demeanor and singular focus earned him a reputation as a reclusive genius. His contributions to quantum mechanics and relativity were groundbreaking, culminating in the Dirac equation, a relativistic wave equation that unified these two disparate realms for the electron. Dirac's equation was a revelation. It not only described the electron's behavior with unprecedented accuracy but also predicted the existence of antimatter, particles identical to matter but with opposite charge. The discovery of the positron, the electron's antimatter counterpart, validated his predictions and opened the door to quantum field theory. This framework, born of Dirac's insights, became the foundation for our understanding of particles and forces, encapsulated in the standard model of particle physics. Despite its triumphs, quantum field theory is built on special relativity, Einstein's theory of flat spacetime. It falters when faced with the curved, dynamic spacetime of general relativity. Gravity, the force that shapes galaxies and bends light, remains elusive in the quantum realm. Attempts to quantize gravity, to describe it as a quantum field, have been stymied by infinities that defy calculation. This failure has driven physicists to reimagine the foundations of reality. The quest for a theory of everything has led to bold ideas, from string theory to loop quantum gravity. String theory posits that particles are not points but vibrating strings, their frequencies determining their properties. These strings exist in a spacetime of multiple dimensions, 10, 11, or even 26, far beyond our three spatial dimensions and one of time. Loop quantum gravity, on the other hand, suggests that spacetime itself is quantized. At the smallest scales, the Planck length, spacetime is not smooth but granular, composed of discrete units woven into a network. To macroscopic beings, this quantum mesh appears as continuous space and time, much as the individual atoms of a liquid coalesce into the illusion of smooth water. But what are these grains of spacetime? Are they fundamental, or do they emerge from something deeper? Here, we encounter the provocative idea that space and time might not exist at all in the fundamental sense. Instead, they could be emergent phenomena, arising from more basic relationships between entities. This perspective echoes the philosophical debate between Newton and Leibniz centuries earlier. Newton viewed space and time as absolute, existing independently of matter. Leibniz argued they were relational, defined by the interactions of objects. Modern physics leans toward Leibniz's vision. In general relativity, matter shapes spacetime, and spacetime guides matter's motion. In quantum mechanics, the wave function encodes relationships, not positions or trajectories. Perhaps space and time themselves are constructs, emergent from the complex interplay of fundamental entities. One tantalizing hint comes from the AD/CFT correspondence, discovered by Juan Meldacena in 1997. This mathematical duality links a theory of gravity in a higher dimensional space, anti de Sitter space, to a quantum field theory without gravity in a lower dimensional boundary. Remarkably, the geometry of spacetime emerges from the quantum interactions on the boundary, suggesting that spacetime might not be fundamental but a derived concept. If true, this implies that at the smallest scales, spacetime dissolves into a sea of quantum information. The universe, at its core, might be a hologram, with the three-dimensional world we perceive encoded on a distant, two-dimensional surface. Such ideas challenge our intuition. If space and time are emergent, what becomes of our notions of existence, causality, and self? Just as we accept that our bodies are collections of atoms, we might need to embrace the idea that our experience of space and time is an illusion, a macroscopic perspective on a deeper, more abstract reality. This perspective transforms our understanding of the universe's end. The decay of black holes and the dissolution of matter are not merely the fading of physical entities but the unraveling of spacetime itself. As the universe approaches its final moments, the grains of spacetime may lose their coherence, leaving only a formless sea of quantum relationships. Despite our advances, the true nature of space and time remains elusive. Theories of everything, from string theory to loop quantum gravity, offer glimpses but not answers. The block universe, in which past, present, and future coexist, might give way to a dynamic picture of reality, where time emerges moment by moment. Or perhaps reality defies our imagination, forever hiding its secrets. As the last observers of the cosmos witness the fading light of existence, they embody humanity's enduring spirit, relentless curiosity, and a profound connection to the universe. Even as darkness claims the stars, their quest for understanding lights the way, a testament to the unyielding pursuit of knowledge. In the end, space and time, so natural, so normal to our experience, reveal themselves as the ultimate enigmas. They are the stage upon which the drama of existence unfolds, yet their true nature may lie beyond the reach of science and reason. Perhaps this mystery is not a failure but a gift, a reminder that the universe, in all its complexity, is as wondrous as it is unknowable. Where are we truly located? Not just your house number, nor the name of your street. Not merely your town, city, or even your country on a continent of Earth. But where is Earth, really? It resides in the solar system, nestled between Venus and Mars. A familiar enough answer. Yet this solar system is more than just its planets. It's a dynamic hub of activity, dominated by the sun's gravitational influence, extending outward into the enigmatic Oort cloud, a vast, spherical shell of icy objects and ancient comets marking the sun's cosmic reach. Still, the Oort cloud is but a minor structure within the local interstellar cloud, a faint mist of gas and dust that itself swims within the local cavity, an expanse of relatively low-density space carved out by ancient supernovae. This local cavity is part of the Orion arm of the Milky Way, a galaxy defined by its magnificent, spiraling arms of stars and cosmic dust, all circling a supermassive black hole cloaked in mystery at its galactic core. The Milky Way spans more than 100,000 light-years, a staggering size on human terms, yet in the cosmic context, it is but a fragment. As we zoom outward, the local group emerges, a collection of 30 to 50 galaxies bonded together by gravity. Among them is Andromeda, a galactic titan twice the size of the Milky Way, hurtling toward us on an inevitable collision course. In a few billion years, these galaxies will collide, their stars pulled and scattered before settling into a new, merged form. But even this cosmic drama is a mere footnote at greater scales. The local group is part of the Virgo supercluster, a sprawling congregation of thousands of galaxies. Yet Virgo itself is dwarfed by the Laniakea supercluster, a monumental structure hundreds of millions of light-years across. Within Laniakea, filaments of galaxies connect like threads in a vast cosmic web, weaving through voids such as the Boötes Void, a chilling expanse 330 million light-years across that holds fewer than 60 known galaxies, a near emptiness in the fabric of existence. As we continue to zoom out, we reach the edge of the observable universe. Here, light has journeyed to us for 13.8 billion years, carrying whispers from the dawn of time. However, the universe's expansion means that the true edge lies much farther, 46 billion light-years away in every direction, forming a sphere 93 billion light-years in diameter. Beyond this boundary lies the unknown. At scales this vast, the observable universe itself becomes a map of grand structure. Galaxies cluster into groups, which in turn form superclusters and filaments. Yet even within this magnificent order, scientists encounter what they term the end of greatness, a conceptual limit to cosmic structures that defies further hierarchy. It begs the question, why is the universe so structured? How did a primordial soup of particles evolve into this stunning array of stars, galaxies, and voids? Was this order inevitable, or is it the result of some profound cosmic symmetry? Even more importantly, how do we know? Mapping the cosmos. The story begins in 1502 with Nicholas Copernicus, a young polymath meant to be studying medicine in Padua, Europe's center for healing. Yet his mind was not confined to earthly ailments. By night, he pored over the works of Aristotle, Plato, and Ptolemy, finding inconsistencies in the prevailing geocentric models of the cosmos. A decade later, in quiet defiance of convention, he drafted his revolutionary theory: Earth is not the center of the universe. We are but one planet orbiting the sun, unexceptional in a vast cosmic dance. Copernicus delayed publishing his ideas for fear of the upheaval they would cause. It wasn't until his 70s, some say on his deathbed, that his seminal work finally emerged, shaking the foundations of science, philosophy, and religion. The Copernican principle, as it is now known, declares that Earth holds no privileged position in the cosmos. This seemingly humbling revelation opened the door to boundless exploration. If we're not special, what else might be out there? Modern cosmology rests on this principle, supported by discoveries like the cosmic microwave background radiation. This faint, primordial glow permeates the universe, no matter where you look. Discovered in the mid-20th century, the CMBR is a relic of the early universe, emitted when matter cooled enough for light to travel freely for the first time. Its uniformity, 2.7 Kelvin across all directions, suggests that, on large scales, the cosmos is homogeneous. Yet here lies a paradox. Our local cosmic neighborhood teems with structure, galaxies, clusters, and superclusters connected by filaments of matter, interspersed with vast voids of near-nothingness. How can the universe be both uniform and filled with such intricate patterns? The answer lies in the interplay of two opposing forces, expansion and gravity. Shortly after the Big Bang, the universe underwent a period of rapid inflation, stretching any initial irregularities across vast distances. As expansion slowed, gravity began to dominate, causing denser regions to pull in surrounding matter. These overdensities grew, forming stars, galaxies, and eventually the vast cosmic web we observe today. But where did these initial fluctuations come from? The first hints emerged in 1989 with NASA's Cosmic Background Explorer. COBE provided the first baby picture of the universe, mapping tiny variations, anisotropies, in the CMBR. These were incredibly subtle, 1 part in 100,000, but they marked the seeds of cosmic structure. This groundbreaking discovery inspired successive missions, each sharpening our view. The Wilkinson Microwave Anisotropy Probe in 2001 and the European Space Agency's Planck satellite in 2009 revealed increasingly fine details of these early fluctuations. Together, they confirmed that tiny quantum irregularities, stretched by inflation and sculpted by gravity, gave rise to the galaxies and clusters we see today. On Earth, telescopes like the Sloan Digital Sky Survey have taken mapping to new heights. Nestled in New Mexico, SDSS collects light from thousands of celestial objects simultaneously, using custom-drilled aluminum plates and fiber optics to measure their distances and motions. This meticulous work has revealed structures like the Laniakea supercluster, our galactic home, and the Sloan Great Wall, a billion light-year expanse of galaxies. But even these colossal structures pale in comparison to recent discoveries. In 2021, astronomers identified the Giant Arc, a structure spanning 3.1 billion light-years, so vast it challenges our assumptions about cosmic uniformity. At this scale, the universe appears as a vast network, filaments of matter connecting clusters, with dark voids stretching between them. This raises a surprising question. What is the nature of this cosmic web? Is it like a soup of meatballs floating in empty space? Or is it more like a honeycomb or sponge, with dense regions separated by voids? Cosmologists have debated these metaphors for decades, not for their whimsy but for their profound implications about the underlying physics of the universe. The truth, as always, lies in the data. By combining observations from ground-based telescopes, space missions, and advanced simulations, scientists are gradually revealing the grand architecture of the cosmos. It is a structure born from chaos, shaped by forces we are only beginning to understand, and filled with patterns that echo across billions of years. And as we continue to map the universe, we may yet uncover deeper truths about its nature and our place within it. As we push the boundaries of our understanding, each discovery leads to new questions. The universe, with its vast structures, appears to follow certain rules, but the full extent of its organization remains elusive. The cosmic web, a network of galaxies, clusters, and voids, suggests a pattern, but what determines its shape? Is the universe governed by simplicity or complexity? The largest structures we see today are a result of billions of years of cosmic evolution. Fluctuations in the early universe grew into galaxies and clusters, but why did those fluctuations exist in the first place? These irregularities are thought to be quantum in origin, tiny uncertainties amplified during inflation. Yet this explanation leaves room for deeper mysteries. What drove inflation? What is the true nature of dark energy, which now accelerates the universe's expansion? One tantalizing idea is that the universe's structure may reflect the geometry of spacetime itself. Einstein's theory of general relativity showed that gravity isn't merely a force but the warping of spacetime by mass and energy. On cosmic scales, this warping creates the scaffolding for the web-like structures we observe. Dark matter, though invisible, acts as the glue that binds galaxies together, while dark energy stretches spacetime apart. Together, they shape the universe into a delicate balance of connection and isolation. And yet, even this balance raises profound questions. Recent discoveries, like the giant arc and the KBC void, a proposed supervoid nearly 2 billion light-years across, challenge our assumptions about the universe's uniformity. Are these anomalies rare exceptions, or do they hint at something deeper about the fabric of reality? Mathematically, the universe's structure invites comparisons to familiar patterns, a sponge, a honeycomb, or a soup. But the true answer may be stranger than any metaphor. The interplay between cosmic forces, gravity, expansion, and the unknown drivers of dark energy and dark matter creates a complexity that defies simple explanation. This complexity is both humbling and inspiring. It reminds us that our understanding of the cosmos is still in its infancy. We have mapped only a fraction of what exists, and the tools at our disposal are improving with each passing decade. Telescopes like the upcoming James Webb Space Telescope and observatories such as the Vera Rubin Observatory promise to unlock new realms of knowledge, from the earliest galaxies to the nature of dark matter. In this grand effort to map the cosmos, we are not just charting stars and galaxies, we are seeking to understand the origins of everything, including ourselves. Every map, every image, and every spectrum collected tells a story about where we come from and where we might be headed. The structure of the universe. In the mid-20th century, as the Cold War raged, two competing schools of thought emerged on opposite sides of the Iron Curtain. In Princeton, New Jersey, a mild-mannered Canadian physicist named Jim Peebles pondered how tiny fluctuations in the early universe could grow into galaxies and clusters. His theory imagined the universe as a meatball soup, matter clumped together by gravity into roughly spherical regions, leaving vast, low-density voids. This bottom-up model suggested that small structures merged to form larger ones, eventually building the cosmic web we see today. Meanwhile, in Moscow, Yakov Zeldovich, a veteran of the Soviet atomic program, was thinking along different lines. Zeldovich envisioned the universe as a series of two-dimensional pancakes of matter. According to his top-down theory, these large-scale structures formed first, with galaxies emerging where the pancakes overlapped, creating filaments and clusters. Between these filaments lay vast voids, shaping the universe into a series of interconnected planes. The two models, meatballs versus pancakes, reflected not just scientific preferences but also the contrasting intellectual cultures of their creators. Zeldovich, constrained by Cold War politics, rarely traveled outside the USSR, so his ideas spread more slowly than Peebles'. In contrast, Peebles' theories gained traction in the West, bolstered by a growing body of observational evidence. But neither theory fully captured the universe's complexity. A new perspective emerged through an unlikely intermediary, Martin Rees, a British astronomer who acted as a bridge between the American and Soviet schools. Rees's postdoctoral researcher, Richard Gott, met Zeldovich at a 1977 conference in Estonia, where they exchanged ideas that would lead to a third, hybrid model. Inspired by both schools, Gott proposed that the universe resembles a sponge, a structure neither entirely clumpy nor flat. In this model, high-density and low-density regions are complementary, connected in a way that balances the competing forces of gravity and expansion. The sponge-like topology suggested that matter and voids were intricately linked, creating a universe that was both complex and self-similar at different scales. As telescopes improved and surveys like the Sloan Digital Sky Survey mapped the cosmos in unprecedented detail, Gott's sponge model found strong support. Observations revealed filaments of galaxies weaving through vast voids, forming a cosmic web. Neither the isolated clumps of Peebles' meatballs nor the flat sheets of Zeldovich's pancakes fully captured this intricate network. Instead, the sponge-like structure provided a more accurate description of the universe's vast, interconnected architecture. Yet, even as these maps revealed the grandeur of the cosmic web, they also uncovered something unexpected, a phenomenon scientists call the end of greatness. Beyond scales of about 1 billion light-years, the universe appears homogeneous and isotropic, the same in all directions. The intricate structures of galaxies, clusters, and filaments give way to a smooth, uniform expanse. This transition raises profound questions. Why does structure vanish at this scale? Why does the universe become so unstructured, so featureless, beyond a certain point? The answer lies in the interplay of cosmic forces. On small and medium scales, gravity dominates, pulling matter together to form the structures we observe. But on the largest scales, the universe's expansion, driven by dark energy, becomes the defining force. The acceleration caused by dark energy stretches spacetime itself, smoothing out irregularities and erasing the clumps and filaments that define smaller scales. This shift reflects a fundamental aspect of the universe. While local regions are shaped by gravity, the cosmos as a whole is governed by the principles of relativity and thermodynamics. The universe's homogeneity at large scales aligns with the cosmological principle, which states that the universe is uniform when viewed from a sufficiently broad perspective. The end of greatness serves as a humbling reminder of the balance between order and chaos. On one hand, gravity creates intricate patterns, weaving galaxies and filaments into a grand cosmic web. On the other, dark energy works to erase these structures, pulling the universe toward an ultimate simplicity. The universe, in its sponge-like complexity and eventual uniformity, invites us to look beyond simple metaphors and toward the profound interplay of forces that shape everything we see. It is a story of contrasts, of gravity and expansion, structure and smoothness, and the ongoing quest to understand a cosmos that defies our imagination. Imagine standing on the equator in Ecuador, gazing up at the night sky with a powerful telescope. You carefully measure the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Now, imagine flying to Indonesia, on the opposite side of the Earth, and making the same measurement. Astonishingly, the temperatures match to an extraordinary degree of precision, differing by no more than 1 part in 100,000. Yet these regions of the universe are now separated by tens of billions of light-years, far too distant to have ever communicated through the exchange of light or heat in the 13.8 billion years since the Big Bang. How, then, could they have arrived at such a precise agreement in temperature? This conundrum is known as the horizon problem, one of the most profound challenges in cosmology. The extreme uniformity of the CMBR, while essential to our understanding of the universe, defies the basic principles of thermodynamics. It suggests that regions of space separated by vast distances must have once been close enough to interact. The solution to this mystery lies in a radical idea, inflation, a theory first proposed by physicist Alan Guth in the 1980s. Inflation posits that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space itself grew so rapidly that regions once in close contact were flung apart faster than the speed of light. This does not violate the cosmic speed limit, as it is space itself, not objects within space, that expanded. Through inflation, the horizon problem vanishes. The regions you observe from Ecuador and Indonesia were once so close that their temperatures could equalize. Then inflation stretched these regions to immense distances, locking in their uniformity and creating the seemingly homogeneous universe we observe today. But inflation does more than solve the horizon problem. It explains why the universe is flat, a property confirmed through precise measurements. Flatness, in this context, refers not to a lack of dimensions but to the universe's geometry. In a flat universe, parallel lines never converge, and the angles of a triangle always add up to 180 degrees. Observations of the universe's density, coupled with measurements of the CMBR, strongly support this flat geometry, a hallmark prediction of inflation. Inflation also provides a framework for understanding the small imperfections in the CMBR, the seeds of the universe's large-scale structure. These slight variations in temperature, amplified during inflation, correspond to tiny differences in density. As the universe expanded and cooled, gravity acted on these density fluctuations, pulling matter together to form stars, galaxies, and cosmic filaments. But where did these primordial fluctuations come from? To answer that, we must consider the strange and noisy nature of quantum fields. Even in a vacuum, emptied of all matter, cooled to absolute zero, and shielded from radiation, quantum fields persist. They fluctuate randomly, creating tiny variations in energy. These quantum fluctuations, magnified by inflation, became the first cosmic seeds, the precursors to the structures we see today. After inflation, the universe continued to expand and cool. Around 380,000 years after the Big Bang, it reached a critical threshold. Protons captured electrons, forming neutral hydrogen atoms. This decoupling of matter and light allowed photons to travel freely, creating the CMBR. But the story of structure building was far from over. As the universe cooled further, baryon acoustic oscillations, sound waves rippling through the primordial plasma, left an indelible imprint on the distribution of galaxies. These waves, driven by the interplay of gravity and photon pressure, froze into place when the universe became transparent, leaving characteristic patterns in the clustering of galaxies at a scale of 150 megaparsecs. Yet the true architect of the cosmic web was not ordinary matter but dark matter, an enigmatic substance that outweighs regular matter by a factor of 5. Dark matter interacts primarily through gravity, forming the invisible scaffolding upon which galaxies and clusters are built. While ordinary matter responded to photon pressure and formed BAOs, dark matter remained unaffected, anchoring the densest regions of the universe. The existence of dark matter was first hinted at in the 1930s by Fritz Zwicky, who noticed discrepancies in galaxy cluster masses. Decades later, Vera Rubin's observations of spiral galaxies confirmed its pervasive influence. Stars at the edges of galaxies moved faster than expected, revealing the presence of a massive, unseen halo of dark matter. Today, dark matter is central to our understanding of cosmic structure, yet its true nature remains elusive. The leading hypothesis posits the existence of WIMPs, but direct detection efforts have yet to yield conclusive results. Despite this, the gravitational effects of dark matter are undeniable. It shapes galaxies, drives gravitational lensing, and determines the universe's large-scale structure. Through the interplay of quantum fluctuations, inflation, dark matter, and baryonic processes, the universe grew from an almost featureless expanse into the intricate cosmic web we see today. From tiny seeds to galaxy-spanning filaments, each stage of the universe's evolution tells a story of balance between chaos and order. And yet, mysteries remain. What is dark matter? What sparked inflation? What lies beyond the observable universe? The quest to answer these questions continues, reminding us that while we have come far in mapping the cosmos, we are still at the dawn of understanding its deepest truths. The story of the universe, while awe-inspiring in its detail and depth, is far from complete. For all that we have uncovered, quantum fluctuations as cosmic seeds, the epoch of inflation, the scaffolding of dark matter, and the baryonic ripples that shaped galaxy clustering, there remain profound mysteries at the heart of cosmology. One of the most pressing questions is the nature of dark energy, the force driving the accelerated expansion of the universe. While dark matter serves as the invisible architect of the universe's structure, dark energy plays the role of a disruptive force, pulling galaxies apart and ensuring that the cosmic web thins over time. What is it? A property of spacetime itself? A new quantum field? Or something entirely beyond our current understanding? This accelerated expansion also raises questions about the ultimate fate of the universe. If dark energy continues to dominate, will the cosmos end in a big freeze, with galaxies drifting so far apart that the night sky becomes dark and desolate? Alternatively, could dark energy reverse its behavior, leading to a big crunch, where the universe collapses back into a singularity? Some theories even suggest a cyclical universe, where each Big Bang is followed by a big crunch in an eternal cycle of creation and destruction. Another enigma is the asymmetry of matter and antimatter. The early universe likely produced equal amounts of both, yet today, matter overwhelmingly dominates. What mechanism caused this imbalance? Experiments like those conducted at CERN aim to uncover the fundamental processes that tip the cosmic scales, allowing galaxies, stars, and life itself to emerge. Moreover, while the observable universe has been mapped with increasing precision, it is but a fraction of the whole. The universe beyond our observable horizon is shrouded in mystery, possibly holding clues to the fundamental nature of reality. Are there infinite copies of our observable universe, as some interpretations of inflation suggest? Or does the cosmos end abruptly, beyond which lies an unknowable void? Then there is the tantalizing possibility of multiverses. If inflation can occur once, could it occur multiple times, spawning an ensemble of universes with different physical constants and laws? If so, how did our universe end up with the precise conditions necessary for stars, galaxies, and life to form? This question touches on the anthropic principle, a philosophical consideration that the universe's properties must allow for observers like us to exist. Even the structure we see today, magnificent as it is, may conceal deeper truths. The cosmic web, with its filaments and voids, reflects the interplay of forces in a universe of 4 dimensions. But what if there are higher dimensions influencing this structure? String theory and related frameworks suggest the existence of extra-spatial dimensions that could subtly shape the universe's evolution. Finally, there is the question of time itself. What came before the Big Bang? Did time have a beginning, or is it an emergent property of the universe's laws? These are questions that stretch the boundaries of both science and philosophy, demanding new ways of thinking and new tools for exploration. The story of the cosmos is one of ever-deepening wonder. Each discovery opens new doors, revealing mysteries that challenge our understanding and fuel our imagination. From the smallest quantum fluctuations to the grandest cosmic structures, the universe beckons us to explore further, to ask bigger questions, and to embrace the unknown. The seeds of structure may have been sown in the earliest moments of time, but the narrative they have grown into is far from over. As we gaze into the night sky, we are reminded that the cosmos is not just a collection of facts but a profound story, one we are only beginning to unravel. And perhaps, in the process, we will come to understand not just the universe, but also our place within its vast and intricate tapestry. Problems with Copernicus. Where are we going? It is a question that has intrigued humanity since the dawn of astronomy. The Earth spins on its axis while orbiting the Sun. The Sun, in turn, spirals around the Milky Way, and the galaxy itself moves through space, pulled by unseen forces. But when we zoom out to the grandest scales, the entire Laniakea supercluster, our galactic home, is moving, pulled toward a point in space hundreds of millions of light-years away. This destination, identified in the 1970s through the study of the cosmic microwave background radiation, was dubbed the Great Attractor. Our local group of galaxies, along with countless others, is rushing toward this enigmatic point at an astonishing speed of 1,000 kilometers per second. But what could be there? What gravitational leviathan lies hidden, pulling such vast cosmic structures toward it? The mystery deepened and astronomers realized that the Great Attractor resides behind the zone of avoidance, the central region of our Milky Way obscured by dense clouds of interstellar dust. Observing this region required X-ray telescopes, which revealed the Norma cluster, a massive congregation of galaxies. Yet, even this cluster could not fully explain the immense gravitational flow. Further investigations showed that the Great Attractor itself is in motion, pulled toward an even greater structure. This new discovery, the Shapley supercluster, lies 650 million light-years away and contains the mass of nearly 10,000 Milky Ways. It is the largest concentration of mass known within a billion light-years of Earth. But the story didn't end there. In 2017, researchers proposed a counterbalance to Shapley, the dipole repeller, a vast underdense region nearly opposite the Shapley supercluster. While it doesn't literally repel matter, its gravitational weakness allows more massive structures, like Shapley, to dominate the cosmic flow. Together, Shapley and the dipole repeller create a colossal stellar river, a billion light-years wide, through which galaxies, including our own, are swept. Yet, this is only one of the peculiarities revealed by large-scale cosmic mapping. Another enigma challenges the very foundation of our understanding, the axis of evil. The CMBR, a relic of the universe's infancy, is extraordinarily uniform. Its temperature varies by just 1 part in 100,000, a testament to the homogeneity of the early cosmos. However, when scientists divided the CMBR into large segments, they found an inexplicable pattern. The temperature differences between quadrants align with the plane of our solar system. This alignment defies the Copernican principle, which asserts that no position in the universe is special. How could the vast, ancient cosmos possibly be linked to our local solar system? Some, like Charles Bennett of the WMAP telescope, suggest coincidence. Others, like Dominic Schwartz, acknowledge its stubborn persistence, even in data from the Planck telescope. This axis of evil remains a mystery, one that gnaws at the edges of modern cosmology. The CMBR is often called the baby picture of the universe, capturing the moment, 380,000 years after the Big Bang, when photons could finally travel freely. But what came before? How did inflation, a period of exponential expansion in the universe's first fractions of a second, begin? One idea suggests a sea of dense vacuum energy in the primordial universe. A quantum fluctuation could have sparked an inflationary bubble, growing rapidly into a universe. If this is true, there might be other inflationary bubbles, other universes. Perhaps they lie just beyond the CMBR, invisible yet potentially detectable through faint collisions with our own bubble. These collisions could leave imprints, subtle anomalies in the CMBR that scientists are actively searching for. The mere possibility of evidence for a multiverse electrifies the scientific imagination. If we could detect such an imprint, it would revolutionize our understanding of reality itself. Where are we in all of this? From the cosmic to the local, our address reads, Observable Universe, Laniakea Supercluster, Virgo Cluster, Local Group, Milky Way, Orion Arm, Solar System, Earth. Each scale reveals layers of structure and order, shaped by simple yet profound principles: gravity, dominated by dark matter, and expansion, now driven by dark energy. These forces transform chaos into beauty. Galaxies swirl in vast filaments, illuminated by the warm afterglow of the CMBR. The collective work of scientists like Copernicus, Shapley, Zwicky, Rubin, Zeldovich, Peebles, and countless others has brought us this far, revealing the intricate dance of matter and energy across the cosmos. Yet, for all that we know, mysteries remain. What drives dark energy? What is dark matter? And what secrets still lie hidden in the stars? The universe is vast, its story written in light and shadow, its answers scattered across time and space. And as we continue to unravel its mysteries, we are reminded of our place within this grand, unfolding narrative, both observers and participants in the endless exploration of the cosmos.